Hey everyone, welcome back, and today let's solve Leetcode problem 1980, titled Find Unique Binary String. So we're given an array of strings nums containing n unique binary strings, each of length n as well, and we want to return a binary string of length n that does not appear in the input array nums. And if there are multiple answers, we do have the liberty of returning any one of them, right? So the key part to note is that we can return any of the length n binary strings that do not appear in the input array nums, and we're also given that all of the length n binary strings in nums is also going to have exactly n unique binary strings, right? So in example 1, we have our input array nums to be 0, 1, and 1, 0. Note how we have exactly 2 of them, and each string also is of exactly length 2, and they're both actually binary, either 0 or 1 for each index. And in this case, our output is 11. There are actually two different possible valid answers for this output, right? Because either we could have 0, 0, 0, 1, 1, 0, or 1, 1. In this case, 0, 0, 1, 1 would still be of length 2 and would still be binary, but those are the two strings that aren't in the input array, so either one of those options would have worked. The output here for the example is indeed 11, although 0, 0 would also technically be correct. In example 2, we have our input array nums to be 0, 0, 0, 1, and in this case, 1, 1 still works because it is binary. It has the same length of 2, and we know there are exactly 2 binary strings in the input array nums, that where 11 isn't in the input array. And since it does not appear in the input array nums, it would be correct along with 1, 0 as well, because that also isn't in the input array nums either. Finally, for example 3, we have our input array nums to be 1, 1, 1, 0, 1, 1, and 0, 0, 1. And in this case, there are actually several different binary strings of length 3 that don't appear in the input array nums, but an option that is valid would be 1, 0, 1, along with these options as well that would be considered correct. So for the constraints here, we see that n is indeed the length of their input array nums. It is actually going to be very small for the context of this input constraints. It's not going to exceed 16, and we're also given that any value n our input array nums is always going to be n, like the problem statement told us, and it's always going to be binary, meaning each index in the input array is either always going to be a 0 or 1, or all the strings of nums are unique, kind of just guaranteeing that we're guaranteed to have valid inputs. Now, this either 0 or 1 kind of leads us to the main observation and the initial naive solution that you guys might have thought of. The main kind of observation to make are, since there are actually n binary strings in our input array nums, and also we know that each binary string is guaranteed to be length n, the number of binary strings we have, there would be a total of 2 to the power of n, or 2 to the n possible binary strings. And if 2 to the n is actually greater than n, which unless n is not equal to 1, or n is less than 1, it's always going to be true, right? Meaning 2 to the n is always going to be greater than n when n is greater than 1. If that's the case, then we know at least one binary string must be missing from the list, because the 2 to the power of n total binary strings would be greater than the n binary strings that we have in our input. So we're guaranteed to have at least one binary string missing. And that also guarantees that a unique string is always going to exist to actually find it, unless n is equal to 1. Right? And that kind of leads us to our more efficient approach, right? The naive solution would just be backtracking. We have two options for each index, either A or B, recursively find or build all of those options and check if they are in the input array nums once we hit a length n string, but that would not be efficient. Instead, a more clever way to actually construct that unique binary string is to use something called the diagonalization method, right? It's even difficult for me to pronounce, so I'm just going to type it out right now. I might butcher the spelling. It's the diagonalization method. It isn't too well known. It's actually inspired by something called the Cantor's diagonal argument. Very advanced words. It's actually not too difficult or advanced of a theorem. Basically, the way it works is we'd take the binary string and we'd take it at some index I, and we'd flip its ith character from 0 to 1 if it's a 0, or if it's a 1 from 1 to 0. And we do this for all of the indices of 0 to 1, or sorry, of 0 to n minus 1 to actually get that kind of unique binary string that we're guaranteed to not exist in the input array nums. And that would also always make sure that the new string would differ from every string in at least one position, right? That would make it, of course, unique. And when I say position, I really mean index, right? So now let's go ahead and actually look at this solution. So again, the solution isn't too crazy. A lot of people may have overthought of this problem using recursion or recursive backtracking. It's actually a lot simpler than that, right? It's just flipping using that diagonalization method for zeros to be ones or ones to be zeros to always get a unique binary string in at least one index, at index I, of course. Right, so the first thing that I'm going to do, I'm actually going to be initializing my result. And as you may imagine, this result is, of course, what I'm going to be returning. It is the unique binary string, and so I'm going to initialize it to be an empty string because, of course, we haven't built it yet. And now let's actually iterate through the input array nums to actually help build that unique binary string index by index, or position by index, iteration by iteration with a single for loop, right? So for I in the range of the length of our input array nums, simply iterating through each index in the range from 0 to n. Right, in this kind of loop here, and I meant, sorry, 0 to n minus 1, not n, right, to actually construct a new string, for each index I, let's actually check if we want a 0 or 1, right? And like we were talking about that flipping method where 0 would become 1 and 1 would become 0. So we get the result, and when I say result, I mean the resulting string that we initialize on line 4, and we'd add to it the string 1. When would we add 1? We'd add 1 if the current value or element in the current string, if it's equal to 0. Right, so if nums at index I, keep in mind this is technically a 2D list. If it's equal to 0, great, we'd add this 1, because of course zeros become 1. But what if it's not equal to 0? So else, that means it's equal to 1, we'd add a 0. Because of course we want to flip it to get that unique character, right? So for each index I, in each iteration of this for loop here, we'd be looking at the ith character of the ith binary string in nums. And it's very important because we know that we have n unique binary strings of length n each of them, right? In the ith character of the ith binary string in nums in the current iteration at index I, if it's a 0 at the current index, the current element, then we change it in the resulting string to be 1. But of course, if it's currently a 1, then we change it in the resulting string at that index to be a 0. And we're appending that flipped character or adding that flipped character to the resulting string, right? And in Python, there's not really an append or .add keyword or method for strings to add elements to it, so plus equals is the way to go. Right, we're basically kind of changing the characters to be a 0 or 1 based on the current index of the current element and the current string, and we append that flipped character to the result, and effectively, once we're done with all of the indices in the entire input array nums, and once we've actually fully built or constructed our unique binary string, we have to return the result, because of course result would store that fully constructed unique binary string that does not appear in the input array nums, right? So if I were to submit this, unless I made any syntax 0, 0, there should be accepted, and there should be a valid solution. And as you can see, this really is just about as efficient as you can get it to be. So again, how does this really work as a whole? How do we actually get an accepted solution on Leetcode? To kind of reiterate how this solution actually works, basically we iterate through the binary strings, right? And we're basically constructing a new binary string by at each index or at each iteration, we're flipping the diagonal characters, either from a 0 to 1 or from a 1 to 0 to guarantee at least that unique string. And that new binary string, we're guaranteed that it is going to be unique because, of course, it is going to differ from each given string at least one position, because for each string in the input array nums, we're guaranteed that we're going to have a 1 if it's a 0 or a 0 if it's 1. We're going to have at least one unique character, either a 0 and a 1 or a 1 and a 0, in every single string, because we're iterating through every single string and guaranteeing that at least one index is different from it. But right, that's the main flipping portion or logic of the solution, right? That always is going to make sure that we do have a valid and correct unique string. So for the runtime complexity here, this is actually going to be a linear solution. It's going to be a big O of n solution. Why? Because really it's just a one-pass solution. We have a single iteration, a single for loop here. We're iterating through the n binary strings once. And of course, within each for loop or each iteration, we're actually performing some constant time operations for each index, but that won't change our runtime complexities. It's just big O of n. And for the memory or space complexity, it's actually linear, believe it or not. It's not big O of n. It's actually big O of 1. It's constant. Sorry, I meant constant, not linear. The reason why is because we're actually using we're really only using a fixed size resulting string, and that can grow to length n, right? So if you guys enjoyed this solution and learned something new, please consider liking this video and subscribing to my channel. And without further ado, I will see you guys in the next video. Bye-bye.